Okay, in this video, we are going to try to compute this sum, and I'm not going to bother to read that. That's the sum. Let's take a look at what we can do. So I look at this and I immediately think, if these don't all have the same denominator, there's probably nothing I'm going to be able to do. So I'm guessing all the denominators somehow become the same thing. I also want to look at the general structure of this and see if there's anything I can do. And I notice right off the bat that in the first term, I have a 2, a 3, a 5, and a 6. 2, 3, 5, and 6 are related. 2 plus 3 is 5, and then 2 times 3 is 6. So I think that I can do something sort of generally here. I'm going to rewrite that first term as the quantity 2 plus 3 plus root 2 times root 3 all over root 2 plus root 3. And then I want to look through and see if I can do that for every term, and I think it turns out that we can do that. For example, the second term would just look like this, right? 3 plus 4, root 3, root 4 over root 3 plus root 4. If we go through and do that for literally every term that's in this series that we're summing up, the final term will look like this, 31 plus 32 plus root 31 root 32 over root 31 plus root 32. Now, the issue is, I don't want to have to do stuff to every one of these fractions. I want to find sort of a general thing that I can do and then just apply that general rule as I go through this. So what I'm going to do is I'm going to try to write it in terms of like n. So where n is almost the term of the series, I'm going to look at the first term that I have here, 2 plus 3 plus root 2 root 3 over root 2 plus root 3. I'm just going to, in my mind, let 2 equal n, which would make 3 be n plus 1, and rewrite this thing, right? So you'll get n plus 1 plus root n plus 1 over root n plus root n plus 1. Okay, so the reason I'm doing this is that I don't want to deal with each individual thing. I want to find a pattern and just use the pattern as I go through. With this, the classic thing to do is multiply by the conjugate. So that's what I'm going to do. Top and bottom by root n minus root n plus 1. At this point, I think I have to distribute. So I'm going to go through and distribute. You can watch that happen. So I did, in my mind, I made it 2n plus 1 instead of n plus 1. So I'm distributing 2n. I'm going to distribute as I go. Here we go. So we'll get minus 2n root n plus 1, and then minus root n plus 1, and then I have to distribute the root n plus 1 across. So that'll give me n root n plus 1, and then minus quantity n plus 1 root n. So that's just distributing. It's annoying, but not really that bad. In the denominator, we just end up with n minus the quantity n plus 1. So it turns out the whole denominator for each and every one of these fractions is -1, which is great. That's what I was kind of hoping would happen. I'm going to clean up this numerator, though. So here we've got things that have root n, right? So you have 2n plus 1, and then you have minus n minus 1, all times root n. That's going to clean up to just n root n. And then you have things that have root n plus 1. So when we clean those up, we end up with, there's a -2, a -1, and then a negative 2n, a -1, and a plus n. So we end up with minus the quantity n plus 1, or really negative n minus 1, but I factored out the negative. All of this is over -1. So I am going to distribute the negative into the numerator, and I will finally end up with each term is of the form n plus 1 root n plus 1 minus n root n. Great. What that means is I can replace all of my fractions with this expression. I just have to plug in the correct thing, right? So the first fraction that I had, I said that n was 2, right? So if n is 2, then this will be 3 root 3 minus 2 root 2. For the next fraction, n is equal to 3, so this will be plus 4 root 4 minus 3 root 3. Now, we can kind of see what's happening here. The 3 root 3 and the minus 3 root 3, those are going to cancel. This is called a telescoping series. And so what I'm going to do is I'm going to write a couple more terms. So the next term, although we don't have it written down, would have been 5 root 5 minus 4 root 4. We got plus ... I'm going to go back one term. So instead of just doing the final term where n is 31, I'm going to go back to a term where n is 30, which will give me 31 root 31 minus 30 root 30. I'm doing that just so the pattern is a little bit clearer. And then the final term here will be 32 root 32 minus 31 root 31. Okay, this is a telescoping series, which means all but finitely many terms are going to cancel out. And we can go through and look at them. So here you got your root 3s, your root 4s are going to cancel, Crucially, the root 2 is never going to cancel. It's just going to hang out forever. Going the other way, the root 31s will cancel. Ultimately, the root 30 would cancel. The only thing that won't cancel is the 32 root 32, because the term that cancels with it hasn't shown up yet, right? We didn't get the minus 32 root 32. So that's not going to cancel. So all that's left over is 32 root 32 minus 2 root 2. Everything can be written in terms of root 2. So I'm going to take out a root 2, and that's going to give me 32, and then the square root of 16 is 4, and then minus 2. And then overall, that will give me 126 root 2. That is the sum of this series. Cool problem. I hope this was helpful, and good luck.